Yeah, I mean, the title is a bit, I mean, the concept of the projects within Mont-Blanc, we are trying to use, say, mobile technology in HPC, meaning in a world in which we have way more powerful chips, right? So, thank you for the introduction, and I want to start with just a quick, say, overview of the idea of the project's timeline, and then going a bit, giving a bit of details concerning the hardware, because we are in this hardware session, with a few experiments that we did lately on the prototype, of the Mont-Blanc prototype. So let's start with the timeline. So Mont-Blanc 1 started in 2011. It just finishes, so we finished to deliver everything in the last week, and in the meantime, Mont-Blanc 2 started, and so we had this period of overlap. So this is a family picture of logos of the Mont-Blanc collaboration or partnership, well, more or less, constant over the time. And as I said before, here is formulated a bit more less poetic way, but so development of a European exascale approach, leveraging commodity and embedded cost-effective technology for tackling the challenge of the exascale. So please note that we have data centers, but we also have ARM and Boole involved in the project, meaning that we have also a relevant industrial part involved. Okay, so concerning objectives, we started in 2011 with 3 objectives. First one was we really want to develop and deploy a prototype based on mobile embedded technology. Second one, we want to learn from this experience. So deploying a prototype raises challenging and raises problem. So we want to learn from this in order to understand how next generation architecture could be. And then we don't want to build a prototype and put it just in a basement, so we have a set of applications that we want to run on this prototype. Then Mont-Blanc 2 started, and here we have, say a sort of 2 ideas. One is to extend the ideas of Mont-Blanc 1, meaning we want to extend the set of scientific applications. We want to extend the support of the OMS programming model, productivity tools, and also the study of the next generation architecture, as said before. Then we want to explore something new, because in the meantime the market and also the success of this ARM idea changed, right? So we want to explore the ARM 64-bit platforms, fault tolerance and resiliency techniques, and explore the markets in order not to develop our own platform that is somehow creating problems and is slow, but also look at the market, the commercial platform that are available on the market. So all this is backed by a dissemination activity called end user group. If you want, I mean, we can talk about this later. So. One question before to start with the prototype. So why are we doing this? This is well known, I think, for most of you. But anyhow, we are seeing in the history of architecture within the top 500 sort of waves of technology appearing. Last big wave that most probably you remember is called x86, that is still dominating the architecture in the top 500, right? So, but if we look a bit more carefully, basically what's happening sometimes is that you have commodity technology that is going back to HPC, right? This is not only true for x86, starting from the desktop, going back to the top 500, but it's also true with other examples. In the introduction was mentioned Roadrunner. It was based on, sort of same chip that we have in the PlayStation 3, and then we know about the success of the GPU. All these are objects that are coming from commodity markets, so basically the game market. in which you have large volumes and at the same time computational capability that can match the requirement of each PC, right? So now the next question is, what is commodity nowadays? Because if we see a huge market and this huge market has a match in performance in what it is required by each PC, so maybe we find something interesting for next generation architecture. And the answer is that, well, if we look at the volumes of the mobile phones and tablets sold in the last 2 years, we see that it's growing double-digit, while server and PC are more or less stable. So, and also performance-wise, if we look, we try to extrapolate a bit. So this the line, the blue line here is, say, the performance of the microprocessor, and this is the performance of mobile processor. So this is also, one could extrapolate that we could have at some point some cross or lines that are going closer and closer. On the other side, you have this nice steep line, and also on the other side the price is low, because these chips are pretty cheap due to the fact that they are sold in a very large volume. So this is basically the, if you want, high-level motivation of the project. Okay. So as I said, we are in the hardware section, so I have a timeline also of the prototype involved within the project. So we started in 2011, still under the hat of praise, building the first prototype made out of ARM multi-core processors. We used an Tegra 2 at that time, and we used a development kit for Android phones integrated in a HPC fashion. So say, take a rack and put a lot of this platform, of this board all together. Okay, so this was very custom made. But in the end, we demonstrated it was possible to operate in a sort of data center way, this kind of platform. And then every year we grow our jungle of prototypes. Most of them are so medium, small clusters. Most of them are, as I said, Android development kits taken and tuned in order to run Linux and our software stack. And we arrived in, say, end of last year with these 2 racks installed and tested in Barcelona Supercomputing Center. So this is the result, so actually the proof of the first objective of the project. First objective was to have a prototype up and running, and actually it is installed at Barcelona Supercomputing Center. And all this history is very important because not only because led here, but also because we had hardware platform in which we can develop software and application. So it is really a matter of having real hardware in which you can improve also the software part. So I want to spend a few more words, of course, concerning our prototype. As said before, we use a mobile chip. It is so fairly old technology right now. So an Exynos dual system on chip. What means that here, inside here, we have 2 cores plus an embedded GPU that are sharing the same memory, so 4 GB of low power RAM. And then we have some local storage, very fast and very high tech, that is in the micro SD form. And then we have some network that is wired through this connector to a motherboard. Okay, so this is our server module that is in a credit card form factor. And we assembled many of them all together in these 2 clusters, in these 2 racks. So we put 15 all together in a blade. So if you visited our booth, you saw it in the last 3 days. Then we have a chassis that is a collection of 9 of these blades, and then we can install as many chassis as we want in the rack. So in the end we have 8 chassis installed. And okay, these are the figures of, say, compute efficiency at the beginning of my timeline in 2011 and at the end when we installed this prototype. And we see that if you look at the gigaflop per watt, we were pretty low at the very beginning. We are getting better, closer to the green 500. But if you look at in this direction, you see that the evolution, I mean, thinking about the lines that we were seeing before, this is a steeper line than this one. So we still have a lot of space in order to improve the energy efficiency here. So this was the presentation of the hardware part, but of course one of the issues also expressed in the introduction, it is how to operate this kind of machine, right? So this is the system software stack that has been developed over the years of the project. So we have, I mean, I don't want to go into details. If you look at, if you have a login and you log in on the prototype, you have exactly the same feeling of running on a standard, say, cluster or standard supercomputer. You have, we have all the cluster management interface, queuing system. We support most of the scientific libraries on ARM architecture. We have developers tools in order to debug and do performance analysis. And we also have the support of the OMS programming model that it can help programming this kind of platform. But if you are old style and you want to just use your own MPI implementation, you can do it. So it's really a platform that allows to experiment. We also have OpenCL support for the Mali GPU, so we can use also the GPU part. And we are pretty satisfied because this is working on our prototypes, but we also tested on commercial ARM-based platform last weeks, and we see that this it is working. So it is really an effort that it's done. It is now available for the community. And here I come back to the comment at the beginning that I really strongly believe that all these challenge towards exascale need to be done within an open source framework, such that the effort that has been done here, that has been somehow painful, can be reused in commercial machines. So this is how we operate this prototype. Is it everything perfect? No, that's not true. We are here also to know the limitation of this platform. So I have a slide in which I summarize the limitation of this prototype. We know that it's only dual core, as I said before. It's very old technology. If we would start today, we could start with octa-core, for example, coming from the mobile world, say mobile market. So this is limiting if you have an application that uses a lot of threads, and we also have just 32-bit memory controller, means that we are just driving for 4 GB of RAM. We don't have ECC protection in memory, so in this sense, resiliency techniques are very useful. This is surprisingly not affecting too much the scalability, as I showed in a few slides later. We don't have DMA support, so we don't have a standard, say, server I/O interfaces like PCI Express or Ethernet on chip. And we also don't have support on chip for the protocol encoding and decoding. So we have to do it. So we have a weak core that needs to also do the extra work of encoding our communication. The protocol of our communication. And also we had some say thermal problems because in our prototype we are running 24/7 like in a standard installation. So all these are not problems because in the history they are already being solved. So we simply have either to wait the next system on chip that will be produced that maybe will solve some of these, or we can design a new HPC by ourselves that is definitely not in the budget of the project actually. So now I have two examples of what means deploying a prototype, and this the kind of problems that you can have when you do something like that. So this is an application. This is the typical scalability plot that you can have, and the green line is the scalability of this application on Mare Nostrum, very nice. And in blue is the scalability on the Mont-Blanc prototype, and in red it was the first run of this very same application, the Mont-Blanc prototype. And you see this, say, very bad behavior that you run on 512 cores, and then you run it again with a double number of the core, and you have exactly the same performance, right? So, and why this was happen, and this is one of the example that I want to show here is, say, is connected to one thing that was, say, mentioned by Gilad before. So the student cluster, I don't know if you were visiting them, they were with a very noisy machine that is one of our chassis, actually. And why it is so noisy? Because we had thermal problems. So actually this problem here, it was a thermal problem that was causing thermal throttling in the frequency of some CPU, and then in the moment in which you have collective operations, you have one chip that is going half the frequency because you pass the, say, the safe temperature of the chip, then all the other chip needs to wait the slow, right? So and you have this effect that we have to fix with a higher frequency of defense. That means that the student needs to come here with a louder machine. Okay, so but I think this is a very important picture because, I mean, these are the frequency of all the nodes. This is a mapping of the temperature. This is a mapping of the power of every single node that Axel will explain soon. So we really have control at node level and also at blade level. Here are the revolution per minute of our fans. So we really have control, and we really can monitor. And this is an important point. This is a second example. This is the scalability, the weak scalability of Lulesh, one of the tools that are say promoted as a co-design tool. Right, so and we can scale till very lot of, a lot of processors in the sense of in the scale of our prototype, say, and say if you do strong scalability, you see a fairly worse behavior, and you see in this area you start losing, right, and then you analyze with some traces, and you discover that you have. At some point, problems in the transmission, so there is a need of retransmission of some package, and then you have retransmission timeout, that is this blue line that is affecting, say, the efficiency, the overall efficiency of your execution. So, message here is that we need tools. I mean, we have platform, but we need tools to monitor this platform. We need tools to monitor the temperature, the power, and also to monitor the behavior of your application in a very fine grain in order to understand the inside. Otherwise, we are building something, but we are not learning from this experience. So, coming back to the project and going towards a conclusion, what we have done. The prototype is done, we've designed it, we've developed it, we've deployed, we are able to monitor. So we also have an HPC software stack that is up and running here. We have a set of HPC, say, kernels and application running. I just show you two of them, but we have, say, a larger set. We also test a non-HPC workload like Hadoop and OpenStack, and we are going to continue in this direction because we know that say, HPC machine can be also appealing in other environments. And what is ongoing, so we are studying, as I said at the beginning, we learn from experience of building a prototype in order to understand how to create next generation architectures. We are investigating the ARM 64-bit say, panorama, also considering acquiring developer board available on the market. And we are porting new application, we are improving the programming model, and we are also monitoring the fault of the current prototype that is up and running 24/7 in order to have insight and understand how we can implement efficient fault-tolerant techniques on this kind of architecture. So this is my, say, philosophical conclusion. I really see Mont-Blanc as like the first move in this in a pool game, right? So and I see that there are balls, say, going all over around. I would say that this is more the direction of Mont-Blanc, in which we try to use mobile technology in order to have, say, a cheap solution for high-performance computing, but you can be also even more extreme if you drop the HPC requirement and you simply say, I want to have a cheap platform to do scientific computation, and you are not bounded by just, or not so bounded by gigaflop, by the LIMPAC and so on. So if we move on the other direction, you start considering this server technology that are coming out, these ThunderX with 48 core, 64-bit. So these are huge chips that can compete with the other that are already in the market. So this is for sure is a more conservative approach. Is lower like the HPC market, and even slower or even more ambitious is to think yourself to a new HPC architecture based on the experience of what we did so far. Of course, here you go in the direction of a cheaper solution, here of a more high-cost solution. And here in the middle, I also like to think that all this technology it can be useful in other environments, and I see the automotive environment like exploding one, but this is something like that I live for. Definitely not related to exascale. So, as I said, the conclusion, the Mont-Blanc project explores the possibility of using the mobile embedded technology for scientific computing. We have hardware contribution, our prototype, we have software contribution, our system software, plus the power monitoring that now Axel will show. And I confirm and I strongly affirm that one of the tools that we need is being able to control new architectures, mean having access to the hardware counter, having access to the power consumption, being able to inspect our application deeply. And okay, so this is the takeaway message after month and month suffering making this prototype working, that even with cheap technology, it is possible to perform decent scientific computing. Thank you very much.
Thank you very much, Filippo.